Dear students, I am Tamil Onan. Now I am going to talk about the problems in heat and mass transfer, especially in forced convections. Then particularly over there is a flow over the cylinders. Okay. Now we move to the problem. Assuming that a man can be represented by a cylinder of 30 centimeter diameter and 1.7 meter height with the surface temperature of say 30 degrees Celsius. Just calculate the heat he would lose while standing in a 36 km per hour wind at a temperature of 10 degrees Celsius. So now we move to the given condition. So in the problem, in the given condition, a man can be represented as a cylinder. So it's just like a man. So then he's having a diameter of 30 centimeter, then height of say that is 1.7 meter. Here the wind is blowing over the velocity. The wind is flowing over the cylinder with a velocity of say that is called as a 36 kilometer per hour at 10 degrees Celsius. So from the problem you can note that first the initial condition is so whether the problem is the forced convection. Why we call it as a forced convection? The cylinder, the air is flow of the cylinder with the velocity. So velocity of say that is 36 kilometer per hour is given. So it's assumed as a forced convection. Second one condition, the problem is there is nothing but there is external flow because the flow is over the surface of a cylinder, that is called as external flow. So given then the given from the given data, the diameter that is equal to 30 centimeter, so which is equal to in terms of meter that is 0.3 meter. Then length or height which is equal to 1.7 meter, and they're having a wall temperature that is a TW which is equal to 30 degrees Celsius. In the problem given it is a 30 degrees Celsius. Uh, 30 degrees Celsius and ambient temperature that is a T infinity which is equal to 10 degrees Celsius. This is the given data. Then for velocity is given as that is u is equal to that is 36 kilometer per hour. Now we can convert it into meter per second. For conversion, we use that 36 kilometer can be converted to meter by multiplying 1,000, and we have converted a hour into seconds divided by there is a 3,600. Finally, we after the substitution we are getting a velocity that is u is equal to that is a 10 meter per second. That is the velocity we are getting. So everything the given data that is converted into in terms of meter. Now we can move to the problem. So in that condition, first we assume forced convection, then we find external flow. Then third one you are going to find that is called as a film temperature. So film temperature is nothing but the average of surface temperature and ambient temperature. That is we call it as that is a 30 degrees Celsius plus 10 degrees Celsius by 2. So finally you can get that is a film temperature is equal to normally that is 20 degrees Celsius. Okay, this is the first condition you find. Next you are going to evaluate the properties of some fluids, properties of that is air. Here the fluid is air. So properties of air at 20 degrees Celsius. So this is find out from the data book, HMT data book that is available here. Um, from the data book, this is the property value. Say it is that on particular atmospheric pressure, gases at 1 atmospheric pressure. We consider this as air. So at a temperature of 20 degrees Celsius, you may note that. So this is at the 20 degrees Celsius, you may note the following properties. So particularly in the forced convection, the properties required is first one is nothing but the kinematic viscosity, second one is thermal conductivity, and third one is Prandtl number. So these three properties are important for the cases of forced convection. So please note it down. From that value, you can find that. So here from the value that is equal to thermal conductivity K is equal to that is a 2.59 into 10 to the power of minus 2 watt per meter Kelvin. Then Prandtl number which is equal to from the property you can consider that is 0.705. Then we have a kinematic viscosity that is equal to 15.06 into 10 to the power of minus 6 meter square by second. So these three properties are important in the case of forced convection. Next condition is you are going to find what about the flow. The flow you have to find out the Reynolds number. Here Reynolds number is find out with respect to diameter because you consider this is a cylinder. from the top you consider this is a cylinder having a diameter of say that is called as a 30 centimeter. Now the air is flowing over the cylinder, you can get the boundary line, you can boundary layer in this direction. So air is flowing the you can get the boundary layer in this direction. So boundary layer is produced across the diameter. So we can use the Reynolds number in terms of diameter. So for that you can consider, so Reynolds number, that is RED, so which is equal to UD divided by mu. That is the kinematic viscosity. Already you know velocity, that is equal to 10 meter per second. So diameter, which is equal to 0.3, okay, 0.3 divided by 0.3 meter divided by kinematic viscosity, which is equal to 15.06 into 10 to the power of minus 6 meter square divided by second. So finally, after the careful substitution of this particular value, you may get the Reynolds number or the diameter, which is approximately, that is nearer to, that is a 2 into 10 to the power of 5. So this is the Reynolds number. Next, we can find the flow, whether it is a laminar or turbulent. With the help of a HMT data book, you may know, from the HMT data book, you may know what about the condition to find out the Nusselt number for particular conditions. Okay. Here in the in the HMT data book, almost near all in the page number, in the convection cases. So here in the convection, there is a flow over external, this external flow. We are going to find the values of the external flow. In external flow, this condition is flat plate, but but our condition is there is a flow over the cylinders. So that is available in the particular page number. There is a flow over the cylinder. In flow over the cylinders, that is across the cylinders, you maybe have a generalized condition, that is Nusselt number at the particular diameter, which is equal to C into RE power D, RE Reynolds number D power M into Prandtl number power 0.33. For C and M, you can refer the particular value. So what about the Reynolds number? You can get it from the value. For our condition, we obtain that Reynolds number, that is which is equal to 2 into 10 to the power of 5. So that may be available in this particular limit. So for our condition, the C is 0.0266 and then M is equal to 0. That is called as a 0.805. So this is the condition. In some cases, this value that may be taken as that is 0.027. So for approximation, here the dm is a coefficient, MC is a constant. You know there is a diameter, D is the Reynolds number. So you are going to find the Nusselt number. So why you are, what is the necessity to find the Nusselt number Nusselt number with respect to diameter, which is equal to, that is a h into d divided by, that is a k. From that you find the heat transfer coefficient. Okay, we write this condition in this data book. So from that is nu, that is d is equal to, that is equal to h into d divided by k. So we are going to find the Nusselt number at the d is equal d which is equal to, already you know the condition, that is c into r e power m into Prandtl number per 0.333. This is a generalized form of Nusselt number in the case of cylinders. Now we substitute the values. Before that, you know what is the C and what is the M. You have a coefficient constant, that is C, which is equal to 0.027. Then M is equal to 0.805. You can substitute the value C and M in the Reynolds number. Then C is equal to 0.027 into Reynolds number I already find, which is equal to 2 into, that is a 10 to the power of 5. Then whole power m, that is called 0.805 into Prandtl number, that is equal to 0.705 whole power 0.333. So after the substitution of this particular value, you can get the Nusselt number, which is nearly approximately equal to, that is a 444. That is approximately nearer to 444. So after finding a Nusselt number, you are going to find the heat transfer coefficient. So you already know the formula. So Nusselt number is equal to hd by k. So already if we find that is Nusselt number, that is equal to 444 approximately, that you don't know, the diameter is equal to 0.3, you know. Then thermal conductivity, that may be equal to, that is a 2.59 into 10 to the power of minus 2 watt per meter Kelvin. So here you are having unit is meter. Nusselt number is a dimensionless number. So dimensionless number. Finally, after the substitution, we are getting the heat transfer coefficient with respect to diameter. So which is closely equal to, that is a 38 watt per meter square Kelvin. So this is the heat transfer coefficient you find. So after finding the heat transfer coefficient, you may find the heat loss. So from the Newton's law of cooling for the convection, for the convective heat transfer. So the Q is equal to He into A into, that is delta T. Here there is A represent, that is called as a surface area. So H into surface area of cylinder, that may be calculated, that is equal to pi, that is a dl or pi dh into delta T, that is nothing but that is a wall temperature minus ambient temperature. H you find from the value, that is 38 watt per meter square Kelvin, then into area pi into, that is diameter 0.3 meter into height, that is equal to 1.7 meter into the temperature, that may be wall temperature is 30 degrees Celsius and then ambient temperature is 10 degrees Celsius. After the careful substitution, you may get the rate of heat lost by a man, there is a Q lost by a man, which is nearly equal to 1220 watts. That maybe approximately 1270. Some cases it may goes to 1200 watt, and some case it maybe goes to 1230 watts, depending upon the decimal value what you substitute for the Prandtl number as well as the Reynolds number. Okay, thank you.